In this video, we're gonna start where we left off and just introducing the sampling, and then take it to the next level and talk about sampling theorem. Sampling theorem basically lays out some groundworks for what is required in order for you to be able to sample a signal such that you can recover that same signal back. So let's go ahead and start with just what sampling really is. Once again, really quickly, this diagram here shows the sampling process where you have an x of t that's multiplied by p of t. P of t is called the impulse train, which is a sum of a bunch of impulses from minus infinity to infinity. They get multiplied by each other, and what you end up with, which is x of p, which is the sampling signal or sample signal, or x of n at that point. So let's go ahead and take a look at that and analyze it both in time domain as well as in the frequency domain. So one of the things we know is that x of p of t is x of t times that. So what we're going to do on this side, let's go ahead and write the equation down. So if x of t is the signal, then the Fourier transform of that would be x of j omega. And then p of t would be p j omega. Now omega s, which is the sampling frequency, and t is the period called the sampling period, so 2 pi over t, that becomes the sampling frequency, where omega t is the sampling period. Okay, and then x of p of t, by the way, x p of t can sometimes is also written the way we're used to seeing it as x of n, which is really x of nt if you want to write it in time domain. But if you assume t is the sampling rate, you can also write in discrete form, and that's basically what a discrete signal is the sample of the signals. Okay, so now the question is, what would be x of p j omega? What would be that in frequency domain? Now we know in time domain, this x of p is simply x of t multiplies by p of t. So if you go back to the properties of multiplication in time domain, it's really a convolution in frequency domain. So xp of t, if I write it as a convolution, is going to be 1 over 2 pi x of j omega convoluted with p of j omega. Okay, and if you want to write it as an integral form of a convolution, if it would be 1 over 2 pi integral from minus infinity to infinity x of j theta. We got to change the variable because that's the variable of integration, and p of j times omega minus theta, and again theta, and d theta is the integration variable of integration. Great. So we have that. One thing also we know that p of t is this. If you take a Fourier transform of that, you will get 2 pi over t summation of k going from minus infinity to infinity of delta omega minus k omega sample. Okay, and we already know what omega sample is. So now if we take this to the next step, we understand that this is basically a delta summation of delta. And if you remember, if a delta function, if an impulse function is multiplied by a function, it takes on the value of that function at that point. So to go back, that means we can rewrite, understanding what p j omega is, we can write xp of j omega, the Fourier transform of our signal, as basically 1 over t, because this 2 pi t over t multiplies by this thing and becomes 1 over t, and then integral of this multiplied by that summation would be just basically x of j at when omega minus k omega s is true. Okay, and this whole thing is in a summation, of course, where the summation k goes from minus infinity to infinity. Again, once again, we are taking advantage of the property of the shifting function or the impulse function, and we're getting basically the function of, we're getting x only where omega is equal to one of the harmonics of sampling frequency. Okay, so that's basically this piece is the result once in frequency domain of when we take a signal and we sample it, meaning that we're going to look at this value in different point, and at that point we multiply it by the impulse and we get the shape of the curve. Now notice you can see the highlight of the curve indicating that these x of n's are basically growing to the size of the curve. All right, great. So we got that. What does that mean? That if you, I think at this point it is important to plot the xp of j omega, so we can take a look at it. So let's say if let's draw this again. Before we get too far, we have to kind of define our x. Since we don't want to pick a specific x, let's say x of j omega, and this is very common in this field, we do that. Let's say x of j omega is a signal, and this signal has frequency contents that range basically from minus omega m to plus omega m. And we basically, what we're saying here, another way of saying this thing is that x of j omega maximum frequency of signal is x omega m. Okay. What we're basically saying at this point, we're basically saying any x of m has 0 values above omega m and below omega m. Great. So now we know what our frequency is. So in this case, it basically says this x of p is describing what's going to be the result for x, the sampled version of this. What would be the frequency spectrum of this for the sample one? The sample one, the interesting thing is, if you look at this, it's going to have basically x is going to get repeated here, and this is going to be omega m and minus omega m, but it's also going to repeat itself over and over again at omega s, at 2 omega s, right, and minus 2 omega s. So what these, except for this one, this is the main one, all these other ones are called aliases. Okay, they're basically said that those signals are aliases or original signals. Okay, so now the thing, the beauty is that if this edge is outside of this edge, all I have to do to recover my signal is basically put a simple low pass. Let me use a different color here. I have to put a low pass filter which omega c, such that omega c is in the middle of between this point and this point, so it can just cleanly cut this out and I recover my signal fully with no degradation. If I even want to get the magnitude back, all I have to do, since the peak, if the peak here is, let's say 1, actually the peak over would be 1 over t, and this would be 1 over t. If I want to pick everything back to the normal one, I can even give it a certain gain and get it back out. But for now, the important part is that our aliases, these guys, don't get mixed up with the original signal. So this is the main signal that we want to get back. and these are aliases. Okay, and we want to kind of get rid of these altogether. And if you do a low pass filter, that will accomplish it as long as one condition is true, and that condition is that these two edges are not overlapped, so it can put a filter cutoff frequency for the filter in the middle of them. So if you think about it, if this is omega s, what is this point? Remember, this is basically omega m, so this point in omega s minus omega m. So in order for me, so this is really important, in order for me to be able to recover the signal, in order for the signal, the original signal, x of t, to be recoverable from sampled signal x p of t. By the way, this is the Fourier series of this is x p of j omega, and Fourier series of this is x of j omega. So in order for me to be able to recover, one thing has to be true. This edge has to be farther out than this edge. So all I have to say is that omega s minus omega m must be larger, not equal. If they're equal, there's an overlap. So it must be larger than maximum frequency of my signal. Okay? So in other words, omega s must be larger than 2 omega m. And this is the essence, this is the sampling theorem. Okay, so this condition leads us to a theorem that I've written down here, but before we get to it, actually we could get to it. It basically says if a signal x of t is a band limited x of j omega equal to 0 for omega larger than that, in other words, the maximum content in the frequency for x of t is at omega m, then the signal is completely and uniquely determined by the sampling at nt, that's basically x of t, if omega s is larger than 2 omega m. This is referred to as, its full name basically is called the Nyquist-Shannon Sampling Theorem, or just simply sampling theorem. Okay, now a couple of other things you need to kind of be aware of. Omega m, the maximum frequency of the signal, this is the maximum frequency content of signal, is commonly referred to with omega m, and this is 1/2 of Nyquist rate, or another way of, so this is called a, let me write it, Nyquist frequency. Okay, so Nyquist frequency is omega m, and then 2 omega m is commonly referred to as Nyquist rate. And basically the sampling has to be bigger than 2 omega m for the be able to recover it. Okay, so that's the sampling theorem. Now the question is, what happens if it wasn't? The problem that happens is that if these conditions are not true, when I'm looking at my x of p of j omega, the sampled version, what I'm going to have, not only I'm going to have my original signal sitting here, if that condition is not true, my aliases creep on, which means there is no way for me to come up with the low pass filter that isolate this. I'm going to pick up some other pieces of the harmonic. This is omega 0, this is omega first sample, the other way. So that's the problem. This is, so I cannot use a low pass filter to recover that, therefore we say this is not recoverable. So the essence of all this, if you want to take one thing away from this, is basically says, if I want to be able to sample a signal and that signal sample to be recovered, so the signal can be recovered from that, I have to make sure that omega, the sampling frequency, is larger than 2 omega m, 2 times the maximum frequency. Maximum signal frequency. Otherwise, I would have aliasing and I cannot recover it. That brings us to the end of this video.